Alright, so welcome to our first video lecture. I'm going to do it this way and give it to you in small videos because I made a larger video, but it took over a day to upload it. So hopefully making smaller, more compact videos, you can watch them each separately. And don't you dare watch this at 1.25 speed to get through this as fast as you can. Alright, so we're going to talk about vaporizers and have the presentation up in front of you to look off of while I go through here. Kind of like class, you watch me read PowerPoints again. So the main thing, obviously anything in bold, is testable. So the key terms, evaporation, comes in a liquid, comes out as a vapor. Evaporation. Boiling point, important to note, temperature at which vapor pressure of a liquid is equal to the pressure exerted by the liquid by the surrounding environment. So we never take that into consideration because atmospheric pressure is always the same. But boiling point is a function of pressure as much as it is temperature. Specific heat, we've gone over before, heat to convert 1 kilogram of a substance, one form to another. The latent heat of vaporization, so pretty much heat, energy, vaporization, or vaporizing. So the energy needed to vaporize a specific substance. So, next slide. So vapor pressure, so what we have, so pressure, force per unit area, vapor is the state that it is in. So it's the pressure that the vapor in the container is when the little vapor molecules are banging off the walls in the vaporizer, is a vapor pressure, function of temperature. Thermal conductivity, measure of how fast a substance transmits heat. High thermal conductivity is desirable in vaporizer construction because, as we're going to go over, you have a dynamic process converting from a liquid to a vapor that takes heat. And if you remember from thermodynamics, heat's going to come from the surroundings, therefore the surroundings will cool, and therefore the system would cool, and it's going to fluctuate the concentration of the vapor coming out if you don't control that going forward. Next slide. So the vaporizers, part of the low pressure system, which we're all familiar with, RV100, did a great job on the project. The SPDD model. So the point is deliver the volatile agent with the mixture of the gas flow to put people to sleep. We want a consistent delivery, something that we can control. So what hazards do we run into, like for first year anesthesia students, like what trouble can we get into? So the main one you could try, filling the wrong agent in the wrong home. It's difficult to do. It'd be like taking a diesel pump at the gas station and just trying to fill your car up with diesel when it's just regular unleaded. I think by the extreme difficulty of it would give you a clue something's not right here. So it doesn't happen as much in the past because you've tried to foolproof this. So if you add the wrong agent to the vaporizer that it was not designed for, we're going to get a little bit wrong delivery here. So next slide. So Dawn kind of started this presentation. So high, low, high. So if you have an agent that has a high vapor pressure, so when we put it in for one with a lower vapor pressure, we will get a higher output of gas concentration. So if you added ISO to SIVO, high, low, high, we're going to get way more than we bargained for. Conversely, high, low, high, low, high, low. So agent with a low vapor pressure added to a vaporizer designed and calibrated for an agent with a higher vapor pressure will give you a lower output. So if you put the SIVO into the ISO for some reason. So on this slide, so the vapor pressure is at 20 degrees Celsius, highest to lowest slide. So again, because temperature and the vapor pressure are interlocked with one another, the temperature at which these values has to be defined. So DES is always an outlier. I mean, the vaporizer is different. The rules that apply to it is different. So it's got the highest vapor pressure of 669. So being that vapor pressure is the temperature at which, now we're changing states here, and atmospheric pressure is 760. It's pretty close to atmospheric pressure here at 20 degrees Celsius. So by that, its boiling point at atmospheric pressure must be really close, which it is. Isoflurane 238, sevoflurane 170. So just kind of remember the order, top to bottom. So if you had desflurane, so des is always the highest, so a high to the vaporizer for ISO, so low, you will get a higher than expected output. So next slide, vapor pressure function of volume, temperature, or pressure, temperature. Just quite simply here, so you have L is liquid, V vapor, with the little VA is not the Veterans Affairs, it's a volatile agent. So pretty much at baseline, in equilibrium, liquid anesthetic to vapor anesthetic, volatile agent here. So we are equal. So if we would increase the temperature, then we shift the reaction. So we had, I'll get to watch me draw. So if we increase the temperature, then we're shifting the reaction in the other direction, getting much more vapor. So we are in a closed container. So the liquid evaporates while it's in there. And there's some molecules leave the liquid and kind of just start bouncing off the wall. So again, that's the vapor pressure of those vapor molecules hitting the walls of the container. So temperature increases, more goes from the liquid to the vapor phase, so we have more vapor bouncing off the walls, so the vapor pressure is higher. Conversely, we cool it down, and there's less molecules escaping, so lower vapor pressure, then lower amount of vapor. So that's why, like in the olden days, so like when Sue practiced anesthesia and you do everything by hand, everything had to be temperature controlled, there would be temperature fluctuation. So, you know, we get more in the vapor, from liquid to vapor, taking heat from the surroundings. The surroundings then cool, then the liquid cools, so we get less. So that it constantly adjusts the temperature themselves. So volatile agents in their bottles, they come in a bottle and we load them in. Before we put them in the vaporizer, they're liquid. We put them in there, fill up to the line, don't overfill them. You're probably going to spill them. I spill them like every day. Sevo does smell, so everyone will know when you spilled Sevo. It's got a little fragrance to it. Sevo and ISO evaporate immediately. If you do work at a hospital that does use DES, DES is a little expensive, so cheap hospitals aren't really going to use it. It's going to be very frowned upon. If you would spill that one, that will bubble a little bit because its boiling point is very close to atmospheric pressure. So, vapor pressure in itself talks about how volatile it is. So DES is like the redhead of volatile anesthetics, like just. So the more volatile, more unstable, quicker they change their state, very hard to predict. Just for Sevo and ISO, a little bit more calm, easy to get along with. You got to push them a little. You got to push them pretty hard to get to their boiling point, make them unstable. So here on the slide with the example of the old kind of black and white is what I showed you kind of earlier of the in equilibrium between the liquid and the vapor. Got the Bunsen burner in the second one, warm it up, get more vapor. The third picture is an ice bath, so you cool it down, shifting the reaction. And the one on the far is if you had, you can't really see it that well, kind of a carrier gas come in, like the flow over gas come in, take the anesthetic with it. So as we're pulling the vapor away, then more from the liquid state goes to the vapor state. So, all right.